just so that, just so that when people ask me questions, I'll just say, watch the video again. I used to say, just read the notes again, so now I can say, watch the video again. Someone left that comment on ratemyprofessors.com and say, all text says is read the notes again. It's no good. All right, so this is the last homework assignment, and it looks a little challenging. So what we'll do is we'll focus on the most tricky, quote unquote, tricky parts of the homework assignment, and go from there. Okay. Oh no, we don't want to. I don't need to know who turned it in. And we'll start with the file. You're given a file that you can download, and then just untar that file. It will give you a folder and a .c file, and then you have to take it from there to complete the homework assignment. So we'll go ahead and do this. Save the file, and then I will decompress it and look at the content. So we'll decompress it to today's folder. How many people have at least taken a look at the homework assignment? Okay, very good. It really helps, if you have already taken a look at the homework assignment, have questions, and then we can talk about it in class. All right, so what I'll do is I'm going to switch to today's folder. And go to the Bean Tree folder. And it creates another Bean Tree folder. And here's the C program. Okay, we'll start with the C program. And we'll start with stuff that we are familiar with already. And then we'll move on to stuff that we may not be familiar with at this point. And show line numbers so that we can now refer to the line. Okay, line 4 to line 8 is the definition of the structure. What you need to do is to take these 5 lines and put it into its own header file. Okay, so you have to take this part out of it to make it turn it into a header file, because you need to share that one header file with another program to print the offset to the include file. In other words, you kind of have to mirror what I did on Tuesday with the linked list program. So in terms of procedure, you have to take it through the same steps. But in terms of the actual code, obviously this one is not identical to the other one. You have to implement all the subroutines except for main. And some of these look really kind of difficult, and some are not as difficult. If you look at this subroutine here, does it resemble the one that we have done on Tuesday? Init node, I think. It resembles it a lot, except this one has a return value. It is returning the same thing that was passed to it as a parameter up here. And are we okay with returning a value like that, returning a pointer? A pointer is also a scalar. It is 32-bit, it fits within EAX, and then you use EAX to return a pointer. Just like with integers and so on. Any questions about this part? How about inside the subroutine? Does everybody understand what I mean when I say count, not count, but if p node? What does that mean? What is implicit and not actually stated here?
Is equal to 0. Not equal to 0.
Not equal to 0. Very good. So this is the same thing as saying if p node does not equal to 0. So you have to compare that to 0, look at the comparison result, and then depending on which end you want, you either use JZ or JNZ to branch around the conditional statement, and that's about it. With the rest, I think we have seen something like this in the previous example on Tuesday. So I think this part is basically just copy and paste, and then change a few names, and you're good to go. Any questions about init tree node? The initialization of a tree node. No questions? Okay. If there are no questions, we'll go to excuse me, insert value to tree, which is kind of complicated in a way, but it's not really that complicated. It has conditional statements, and This is an outer conditional statement, and then within the else of the outer conditional statement, we also have an inner conditional statement. The condition of the outer conditional statement is to compare whatever p root points to and see if that is 0. In other words, I could have replaced this statement with not exclamation point asterisk p root. It would have meant exactly the same thing. But in this case, I compare that to the null pointer because that's exactly what I want to know. Is it pointing to a null address, which basically means there's nothing in the tree at this point. Is that okay? I mean, are there any questions about this part? No questions? Okay. Let's see. How do we do this part in assembly?
I don't know. Let's talk about it.
Let's talk about it. Very good. All right. It is a subroutine call. Okay. We know we are calling init tree node, which is our own subroutine. But whether it is our own subroutine implemented in assembly or whether it's a subroutine implemented in C should not matter because we are doing everything that conforms to the standard of GCC. Okay. Let's take a look at the first parameter. The first parameter is this part here. It looks really long, but it's not really that bad because the first parameter is really the return value of malloc. This part here is not, you cannot do a single thing about this part. This is type casting. It's casting a void pointer, which is returned by malloc, to a pointer to a struct tree node. There's no equivalent operation in assembly language programming because a pointer is a pointer in assembly language programming. A pointer does not have a type associated with it. An address does not have a type associated in assembly programming. So this part, there's nothing to worry. There's nothing to do with this part. What about this part here? This is the parameter passed to malloc. It tells malloc how many bytes we want to allocate. Do we have something similar to this once you have the header file or the include file done? Yep, we have the size of the structure, so you just pass that on the stack, call malloc, and malloc is going to return a pointer. Anything that returns a pointer is returning that in EAX. So what you have to do is to push EAX, as the first parameter, but you have to do that after you push the second parameter on the stack first, because we push parameters in the reverse order. So in this case, we have to push parameter B on the stack, and then the return value of malloc on the stack, and then you just call init tree node. Whatever that returns, you have to put it into wherever p root points to. Are we doing okay so far? Okay. Now, one thing that you might want to do is not to start the assembly code, but go into GDB and look into, trace this program line by line until you are familiar with what the program is actually doing. Does anyone want me to describe how binary search trees work? Because it's just a general overview that might be helpful. Okay. So let's go ahead and do that part. I can only do it on the whiteboard because otherwise I'll be spending too much time struggling with the tools and whatnot. Well, actually, maybe that's not too bad. Maybe I can do it in Inkscape. Because this way I don't have to copy the stuff from the whiteboard, and it should all work out. Change it to letter size and make it landscape. And by the way, this is a great tool for freehand drawing. All right, so what a binary tree is something like this. This is the root of the tree. The root of the tree is nothing more than a pointer to a tree node. If you have a tree that is empty, in other words, there are no nodes, there's nothing stored in the tree, this thing points to null, is the null pointer. It doesn't point to any particular node. If you do have any tree node, I will use a circle to represent it. Then you have a node like this. Now the thing about the binary search tree is like this. Let's say we have a tree. Okay, let me delete this part first. This is an empty tree, it is not pointing to any particular node. So when you create the first node, when you feed it the first number, you create the first node like this. And then we can say that this tree node has a particular value, and we'll just call this, let's say 5. 5 is the first number that you enter into the system. I think the color is not working out, because the projector is really old and somehow they took it away. That's better. And then we'll. That's better. Okay, so 5 is the first number. The next one number, let's say we have 3 coming in. Now when you, let me draw a pointer first. So where's my pointer tool? And then I have to go to stroke style, go to hand marker. Oh, that's too small. Big one. There we go. Okay, so the first node is 5, and then 5 as a node is going to have its p left and its p right pointing to null, okay, to indicate that there's nothing after this 5. If the next one coming in, it has a value of 3, anything that is less than 5 goes to the left-hand side. Anything that's greater than 5 goes to the right-hand side. So 3 belongs to the left-hand side, and we can see that there's nothing on the left-hand side, which means 3 is going to be on its left-hand side. So we'll go ahead and duplicate, move this one over, and then change our 5 to 3. Draw our pointer. This is our P. I think I got it reversed here. This is actually a P right, because in the program I use P right to point to the smaller value. Okay. So at this point, 5 it has the other pointer pointing to null, and 3 has both pointers pointing to null. Are we doing okay so far with this? What if the next one coming in is 4? Where do I put 4? Anything that is less than, we put it on the left-hand side. Anything that's greater than, we put it on the right-hand side. If 4 comes in, should I put 4 over here? No. So 4 has to go onto this side. But this is already taken. 3 is already taking this place. But I can put it to the right-hand side of 3. So when 4 comes in, it's going to be here. Okay, and then we can draw another pointer. So here to here. Like so. Are there any questions at this point? What about 6? What if the next number coming in is 6? I'm reading all these numbers from standard in, by the way. So if the next number coming in is 6, where does it go? It goes to the right-hand side of 5. But there's nothing there at this point. In other words, that particular pointer of that tree node is null at this point, which means there's nothing at that point. So that means 6 can basically go to this place here. So when 6 comes in, it's going to be over here, and then we can change this to 6. And then draw another pointer. Like so. So that's how we construct a binary search tree. Are there any questions about the binary search tree itself? Yep.
What if we have another 4?
According to the algorithm, if you have another 4, or if you have a number that is already in a tree, nothing is going to be done. Basically, the insert algorithm will keep going until it finds that value, and then it will just say, oh, the value is already represented in the tree, and then it doesn't do anything about it. Yep.
So then how does the tree end up displaying these values? I know it's in order, but how does it go about doing it?
How does it go about doing it? That's a very good question. This is the power of recursion. Okay, the power of recursion has to do with looking at things and say, when I break this big thing into smaller things, each smaller thing looks structurally the same as the bigger thing. Okay, so what you do is this is the first node. This is the root of the tree. It points to the first node. The first node says, well, I don't think we should print this value first, because we have to print all the smaller values, and then me, and then all the values that are greater than me. But because of the property of a binary search tree, that's pretty easy to do. Because in this case, we can just say, oh, I don't know, when I should be printed, but I know that everything to my left-hand side are smaller than me. So why don't I, tell the tree on my left-hand side and say, print everything that you have first. I don't care how you print it, but print everything that you have first. When that returns, then it's my turn. And then I also know everything to my right-hand side is bigger than me. So after I print my own value, it is time to print everything to my right-hand side. Is that making any sense? So when you look at the algorithm, it reflects exactly that. Because when you look at the algorithm to print out everything in the tree, it's basically saying, am I a valid node, okay, or am I an empty tree? If I am an empty tree, that means I don't have a node, I don't have anything to print. So that's why you always have to check that you are not an empty tree first. If you are a tree that is non-empty, then the first thing you do is to say, oh, okay, if I'm not empty, I will print everything to my left first. Because the left-hand side of the tree represents all the values that are smaller than your own value. It may be an empty tree. Maybe there's nothing to print, but it doesn't matter. You just say, okay, whatever is on my left-hand side, print it first. And then you print your own value, whatever that is, and then you print whatever is on your right-hand side. So I did not actually mess up in the program. Left-hand side is smaller, right-hand side is bigger. Is that okay? But how do we print everything to on my left-hand side? Well, it's the same subroutine. Okay. So that's why this particular subroutine works, and it looks really, really simple because the data structure is already set up correctly. Now, when you look at the insertion, the insert call, insert value to tree, it's pretty much the same thing. The first thing it checks is this an empty tree? Because if it is an empty tree, then there's not much I can do, because I'll be the only node of the tree. I just have to make sure that the root points to this node, and that's the end of it. Any questions about that part? Now, on the other hand, if I'm not an empty tree and I have to insert an additional node to the tree, I have to go through the logic here. Because what I'm doing is I'm looking at the node at the root of the tree and say, okay, what is your value? Because by comparing that value, I can see which way this new node is supposed to go. If the root of the tree, or the root node of the tree, has a value that is greater than v, I know that the new one, which is smaller, is supposed to go to the left-hand side. If it is bigger, if the new value is bigger than the value of this node, we know it has to go to the right-hand side of this tree. And once again, we are using recursion to basically use the same logic to insert a new node, but into the subtree of the main tree. Are we doing okay so far with the basic logic of this algorithm? You will see this again in cisp 430, and Mr. Fox will do a much better job than me explaining this, because he will probably spend a whole class talking about this instead of 10 minutes. But then he'll ask you to write the algorithm too, where I give you the algorithm in this class. If this is one of your homework assignments, turn in your assembly code and see what happens with Mr. Fox. Well, you just have to read the instruction carefully in his class. If he doesn't say specifically to implement this in C++, hey, you didn't say in which language. I can do it in assembly.
It does.
Ah.
I think somebody's tried it before.
Somebody tried it before.
Yeah. It actually doesn't matter. It'll just give you 0.
Before I trip myself. All right. Are there any questions about this code? The basic logic of it? Okay, let's go to build tree. Now, build tree is actually non-recursive. This is the only non-recursive subroutine that you have to implement, but it looks kind of daunting because it seems to have elements that we haven't talked about in the class. Well, let's go ahead and take a look at this algorithm and find out whether we can do this or not with everything that we have learned so far. It takes one parameter. Can we pass parameters and access the parameter in assembly? We can do it. Okay, this is the first obstacle. What do we do with something like this? Well, the first thing is you have to pass this as a parameter. How do we pass parameters? We pass it on the stack. We push it on the stack. But what is standard in? Well, if your C program knows what standard in is and it is not a macro definition, your assembly program will also know what it is. The linker will resolve it correctly. Okay, so that's one thing that you have to remember is the linker will resolve this. Now this is a parameter to the subroutine called FEOF or end of file. It checks whether you are already at the end of the standard in file. Okay. Do we know how to call a subroutine? FEOF is a subroutine. You may not know where it is, but the linker will find out where it is. So all you have to do is to say call FEOF. The assembler doesn't really care because the assembler will just say, oh, this symbol, I don't know what the definition is, and it will pass it on to the linker and have the linker to resolve it. And the linker will resolve it if you use GCC to link it. What about the exclamation point? What does it mean? Not, okay? So when do you think FEOF, or what value do you think FEOF has to return to make this statement true?
0.
Yep, it has to return 0 to make this statement true, which means you have to compare the return value of FEOF, which is a single integer. It is stored in EAX. So you compare EAX to 0. If it is 0, you stay in the loop. If it is non-zero, you get out of the loop. Because we get out of the loop when we are at the end of the standard in file, so that we don't take any more numbers in. So I think that part, that explains how to perform this particular loop. Let's look inside the loop. We have never talked about. Okay, let's talk about this one first. Can we deal with the address of v, which is a local variable? We talked about that. Okay. So instead of passing v open paren EBP close paren on the stack, you have to pass the actual address on the stack. But we talked about how to calculate the address of a local variable already, so you just kind of have to go back to the notes and find out how to do it. I can see how people keep complaining about that part in ratemyprofessors.com. All right. How about the literal string? %d as a literal string. Which construct do we use to make %d a literal string in assembly language programming? .asciz, okay? ASCIZ is the directive that you need. You can also use .ascii, .ascii, and just manually do a .byte, 0 at the end, right after the string. Either way works. But you have to refer to the address, so you have to put a label on that line of .ascii or .ascii so that you can refer to the address of the string. You push this on the stack, then you push the address of the string on the stack, and then you just call scanf. What scanf does is it interprets it reads from standard in, and then it tries to interpret that as a signed number, a signed base 10 number. Okay. And it returns a value. It returns 1 if one thing is interpreted. But since I'm only asking for one thing, when it returns 1, it simply means that I just read a number. I read a number that can be interpreted as a signed decimal number. Are we doing okay so far with this part? Okay. For everything else, we just don't do anything. We just ignore. So you can turn the switch statement easily into a conditional statement. If scanf returns 1, do this, and then else, there's nothing else to do. Are we doing okay so far with this? Okay, and that's build tree. So that covers all 3 subroutines. Any specific questions up to this point? Yep.
Can we briefly talk about the offset file, the char pointer specifically?
The char pointer. Okay, so you're talking about. Okay, let me open up a new tab. So you're talking about the one thing that we talked about the other day.
Yes.
You're talking about let's see, struct node.inc.
I'm always talking about it.
You mean this is? You mean this part?
I tell all my friends.
Or are you talking about the program that prints it?
I'm talking about this.
Okay. Good. All right. So the question is, what is this expression doing?
Yes. Can you just explain that?
Okay. Well, we'll start with n, because everything starts with n in this particular construct. N is my local variable, which is a struct node. It's a local variable. It is a struct node, so it takes up, in this case, I think it takes up 12 bytes. Either 12 bytes or 8 bytes, I cannot remember. Okay, is that okay? But the address of does not work on n. The address of is applied to this entire thing. In other words, if I want to use parentheses to indicate the order of operation, the ampersand is actually working on this entire thing in parentheses. Okay. So we know what n is. We also know what is p next. P next is a member of n, which is a node. Okay? So this is trying to find the address of the member p next of n. Now, what is the address of p next? What is the type of the address of p next? Let's take a look at node.h. P next itself is a pointer to a struct node. So the address of p next is actually a pointer to a struct node. Are we doing okay so far?
Kind of.
Kind of. Okay. But we know that the entire type of this part is a pointer to a struct node.
Okay.
Okay. What is the type of? Oh well, I highlighted the wrong part. Not including the char pointer, it is a pointer to a struct node. That's the type of the pointer. What about this one? N itself is a struct node, so the ampersand of n, or the address of n, is a pointer to a struct node.
Yeah.
So that means the 2 pointers are incompatible. I cannot do a subtraction because GCC will complain the types of the 2 pointers are different, and you cannot take the difference between 2 pointers when the types are different.
Okay.
So what char star does is to cast both of those pointers into particularly a char pointer, because a char is a byte. So when I do the subtraction, I will get the number of bytes in between and not the number of 4 bytes in between. So that's why we have a char pointer as a cast, so that we can count by bytes and not count by 4 byte increments.
Okay.
Yeah.
So when you say the p next is pointer to the struct node, right? And then it's gonna point to the first byte of the struct node, right? The p next gonna point to the first byte of the struct node.
Well, at this point, this is not even initialized. N is not initialized at this point, and I don't even care about the content of n, because all I really want is the address of individual members of the structure n.
So just say the p next is a struct node. So the p next gonna point to the first byte of the struct node, right?
Correct.
All
Yes. It points to the beginning of the next struct node. Yep.
So you could you have passed one of those to the type of the other one and subtracted it?
Then you will have to multiply the difference by 4, because the size of a pointer is 4 bytes. When you subtract 2 pointers, then it is only telling you how many things are in between, not how many bytes are in between. And in this case, I'm interested in the byte offset, I'm not interested in the number of 4-byte thing in between.
I don't get that. What do you mean by 4-byte thing in between?
All right. Well, let's take a look at another program then. Let's go back to today's folder. I can write a sample program to illustrate that. I'll call this pointer div, pointer dove. Too much Simpson. And I don't even have to do much with this program. All I have to do is okay, let's do something like this. Struct x, and inside the struct x we'll have a buffer of 12 bytes, an int, and okay, that's it. Okay, so the question now is, what do you think? Okay, I'll have an integer I, and I'll say we'll have a struct x array, and we'll just call this array, and it has 5 elements. So the question is, what is okay, what do you think is the answer? What do you think is the value of I after this statement?
8. 3 bytes.
8 is a 2. Because it's counting how many struct x are in between those two addresses. Okay, let me say that again. The number of bytes in between is actually not 8 bytes because the structure has 12 bytes plus 4, so each struct x actually has 16 bytes. In terms of number of bytes between these two, it's going to be 32 bytes. But when you do a pointer subtraction in C, it is type sensitive. So it's not telling you the number of bytes in between, it's telling you the number of things in between. In this case, one thing is a struct x. So it will tell you 2, I is going to equal to 2 after this subtraction. On the other hand, if you cast the pointers, each one to a pointer to a char, because a char is one single byte, this time it will be counting bytes, because it is still telling you how many things are in between, but because of the typecast, each thing is a character or a byte in this case, so it would count the number of bytes in between instead of the number of struct x in between. Okay? Sorry?
This would be 32.
In this case, it will be 32. So just to be sure, I'll go ahead and run this program in GDB. Oh, okay. All right, so we'll run this program in GDB. gcc-g-o, pointer div.c, gdb pointer div. We'll put a breakpoint on line 11 and just run the program. We'll single step through line 11, print I, it is exactly 2, because we have 2 struct x in between. And then if I single step again on line 12 and print I again, this time it's 32, because it depends on what you are counting. What is one unit? What is the unit that you're using when you're counting these bytes? So that's why in the program print struct offset, or whatever you have to implement to print the offset, you have to cast all the pointers to chars or char pointers so that we are counting by bytes and not counting by any other units. Okay, is that okay?
Yes.
All right.
That's great.
Excellent. Yep.
Is that the only type we could cast as? Is char the only thing we could cast as, so that it will count by?
You can cast it as a int 8_t, because those are basically aliases of a char. Unsigned char would also work, because it is just a char, except it is unsigned instead of signed. So unsigned char, int 8_t, uint 8_t, they should all work. Any other questions? No other questions? Well, if there are no questions, we'll go back to this code and we'll just cover one last thing, which looks, kind of particularly nasty, which is this part here. Okay. So how do we I cannot give you the code because if I give you the code, they'll like half the homework assignment is done. you can see how often we refer to something like that, right? So the question is, how do we go about doing this? Well, you start with where do we start? Well, you start with the innermost thing, which is p-root itself. Okay. Now this is p-root. But I'm not interested in the value of p-root. I'm interested in what p-root points to. What is p-root pointing to? What is the type that it is pointing to? Okay, let's take a look at the prototype. P-root itself is a pointer to a pointer of a struct tree node. So what is the type of this part? A pointer to a struct tree node. Okay. What can I do with a pointer to a struct tree node? Well, no, not quite. It has a member that can point to another struct P node. So when you look at this part here, it is basically saying I have p-root. I use p-root to get to a pointer to a struct P node. But of that struct P node, I don't want the entire thing. I just want P left as a member. But I don't want the value of P left. I want the address of P left. Because the address of operator is outside the outermost parentheses. So I'm applying the address of this entire thing. Okay, let's draw a picture. Let's make sure that we can understand what we are talking about. Pictures. Picture is good. All right. So what we'll do is we'll kind of reuse parts of this picture. This is my p-root. Okay. P-root points to another pointer. So I have another pointer over here. And then we'll go ahead and draw an arrow here. Okay. This is a pointer. It points to a struct P node. Okay. So we'll go ahead and draw a struct P node, which looks like this bubble, but the bubble doesn't really show you the internal structure. So I will make this a little bit better and draw the actual thing. Okay, so this is a struct P node. A struct P node has tree node. In this case, it's a struct tree node. So we'll go ahead and draw the pointer first. The pointer is always pointing to the beginning of the entire thing. Okay. Within a struct P node, we have several things. We have the value, and then we have P left, and then we have P right. So we'll go ahead and draw those three components here. We do want order. Three components. Depending on the ordering. Now, do not use a hard ordering. Always use the symbolic name to refer to the offset to the right ordering. So we'll have these labels saying this. Let's say this is P left. This is P right, and this is B. Okay. So what we want is the address of P left. That's what we want. So if I want to indicate the address that we are interested in, it will be this address here. Change stroke style. That is what we want. That's what we want to push on the stack as our parameter is what is this address? So in terms of assembly programming, we are starting with p-root, but our p-root in assembly programming is actually the offset from where EPP points to the parameter p-root. So you got to remember that this thing, this portion here, I should use the mouse pointer because otherwise, when people watch the video again, it's like, which one? What are you talking about? This is what we are talking about. So this is on the stack. This is a part of your call frame. It is your parameter. Your parameter points to, a 4-byte thing, which is a pointer. But that's not what you want either, because that's just the address to find the struct p node that we are interested in. We are not interested in the beginning or the start address of the entire struct p node. We are only interested in the address of the member p left of the struct p node. Okay, so you need a few steps, to calculate the address of the p left of the structure pointed to by a pointer that in return is pointed to by p-root, which is a parameter passed to you. Is that helping? I think what you can do is look at this picture, and then each time you have a pointer like this, and also you're going from here to here, it is a particular construct in assembly language programming that you have to do to either to follow the link or to add the offset. So you just have to track it down with the right thing, and then do it by hand first. Do it by hand in GDB. Do it by hand. Once you can do it by hand, then you can do it in assembly. The other thing you can also do is to do it in GCC. Run the entire program without doing any conversion. By the time you get to that part, print the ampersand of the entire expression and see what it is. And then you want to track down, okay, if I do everything by hand, how do I get to that part? Okay. Any questions about this part? Should I kind of demonstrate how to get started with this program using just GCC and the C code? Yeah. Okay. Let's get this out of the way and start with the C code here. So gcc-g-o bin3 bin3.c gdd bin3. All right. So which part of the program do you want to take a look at? Insert into tree. Okay. So we'll put a breakpoint on, let's say, line 30. Okay. When you run the program, you have to feed the program, numbers. And in order to make sure that we are going to insert something to the left branch, we'll start with a value of 30, which takes up the root. This is the first node. And then we want something to the left-hand side, so a value smaller than this one would do. So we will try 13. Okay. And sure enough, that will get us to the breakpoint. So what you want to do at this point is to print what is p-root. Okay. But how did I get p-root? I got it as a parameter, and this is a good time to use backtrace to see where we came from. And when you use backtrace, you can also say frame, in this case frame 2, so that we change our frame back to the main program. And this is how Subroutine got its parameters. It's the root local variable in the main program is is that. But this number or this address does not match this address here. What is wrong with it? Because it's the address of that. So this way you can track down everything, and see, how in the subroutine insert value to tree at this point, how did we get p-root to be like that? Are we doing okay so far? Okay. So now we can change the frame back to frame 1, back to this point. Oh. No, we want to change back to frame 0. Frame 0. All right, so now that we know what is p-root, we can also print, okay, we can say print p-root, it is this number. We can say print the asterisk of p-root it is the address of a tree node. And once we get to the address of a P node, we can now finish the entire expression and say what is the address of this entire expression. And it's the same because I think left is the first member of the entire structure, and that's why it is the same. Okay. Any questions about this? So if you look at the picture and use GDB to track it down as you look at the picture, that should give you a pretty good idea of what you have to do, at least by hand. But once you know how to do it by hand, then you can use assembly programming to help you. I can give you a few hints. In the calculation, all you need is indirect. You take you put the address into a register, and then you take the indirect of that thing to get you the value that is the referencing to. And then at some point you also have to add the offset, because you're trying to access the address of a member of a structure, not the beginning of the structure. So by the time you get to the address of the entire structure, the next thing you have to do is really just to add the displacement of from the beginning of the structure to the member, and just add it to the address of the structure. Then you have the address of the member of a structure. I don't want to write it down, because once I write it down, the whole thing is like, oh, okay, it's all done. Yep.
So then 0x8 is the beginning address of a structure?
This one is, and this one is not. Because this one, according to the type, is the address of a pointer.
Yeah.
This one, on the other hand, is the address of a tree node. So you can actually dereference it if you want to. In other words, if you want to, you can say what is the dereference of a key root, and that is a structure. Okay. So GDB can be quite useful because when you compile a program in C and you run it in GDB, GDB understands the concept of types. So that's why you can, when you dereference to an entire structure, it knows, how to print out the members of the structure. And this also confirms that P left, was the first member, and that's why the address of P left turns out to be the same as the address of the entire structure, because it is the first member of the entire structure.
So on the stack, it would be the last thing.
On the stack, it will be the lowest thing.
Yeah, the lowest.
Right.
It's the last.
But we are not passing this on the stack. So you should only say in memory it has the lowest address.
Because the only thing we're putting on the stack is
Or
the pointer to
the pointer.
that.
Exactly. The structures are all allocated from malloc. So they're all coming from the heap. And you can tell the addresses are kind of off, they're kind of different, because when you look at this one here, this is allocated from, let's see, what is that allocated from? This one is allocated from the heap already. And that's why you can see the address is a little bit different from this one here. This one is stack-based. This is actually our root variable, local variable root in main. And that's why it has a very high address, because it's in the stack. This one is actually allocated from the heap, and you can see that the address is entirely different. Any questions about this?
Can we put 13 on, or just go through until?
Yeah, we can. Well, we just inserted 13, and that's why we stopped here.
Oh, we did.
Yeah, we did.
Okay.
Well, it is in the process of inserting 13 into the tree, and this is the first step, because it's recursive.
Right.
This is the first invocation. It will invoke itself again. The second invocation will find a place to actually put the node. Yep.
My question actually has to do with the schedule for next week, but relates to the project, because it's due on Thursday, right?
Correct.
And I heard from another instructor that Thursday no one has class because this is the beginning of the first finals. Is that true?
That is true.
Okay, so hypothetical situation, I'm like panicking about this project because I can't get it to work. Like on Thursday or around Thursday, is there a way
I will have office hour posted on the door, so every day in the final week I will have office hours. And I think I'll make my office hours from 9 to 10 for each day. So I'll be in my office from 9 to 10 during the final week.
That'd be
AM. PDT, Pacific Daylight Saving Time. Just so that we don't use accidentally use UTC as time for timing purposes. Yeah.
Just a question about GDB. After you've done like sifting through the program, is there a way to display the next command to be, or the next line of the code again?
To split.
So you know how you had a breakpoint, right? It says,
Yeah.
oh, this is the next one's going to be executed, right?
Right.
But then I'm going to mess around it for about 20 lines, and I'm going to forget what the damn thing is next. Is there a way to display it without having to like sift through all the stuff I've done?
Understood. There are several ways to do it. Okay, so I'm kind of, if you use a BT backtrace, we kind of know where we are. Main called build tree in return called insert value to tree. So let's just say that you're not interested in the rest of the execution of insert value to tree, and you just want to get back to build tree and continue tracing in build tree. Okay, so let's say that's what you want to do. So what you do is you say frame 1. We know the frame number because they are all numbered here. So you go to frame 1. But now we are in build tree. So you say list build tree, and build tree is here. And let's just say that we are interested in the switch statement itself. Okay, we want to stop again on line 54. So you say B54. You put a breakpoint on line 54. And then all you have to do is to say C to continue execution at full speed. Now in this case, it will stop again because I put a breakpoint in insert node already. Well, it won't break again because it's not going to go to the left branch again. So it won't stop again in insert value to node. Instead, now it will stop on line 54 of build tree.
Oh, okay, so that's what like looking at the whole program. But I mean, like, is there a way to show where I'm already stopped at, like my current breakpoint, I guess?
Your current breakpoint?
So, okay, we're at this point now. It says 54 switch. It's the next thing to be executed, right?
Right.
Now I'm going to do a bunch of searching to figure out what's going on, and I'm going to forget where I'm at. Is there a way to go back and say, oh, this is the next thing to be executed?
Okay, I see. Help. Okay, I think it's okay. Let's trace point, tracing without stopping, user defined, support, status. It's either status or running. I think it's one of it. Either running, breakpoint. Okay, let's do it alphabetically. So help breakpoints, break range, catch, command condition, ftrace, ignore. Okay, I don't think it's. No, a watch is a watch expression, and that's basically it prints that value. It evaluates that expression every single time you say single step. It's really useful when you want to track down, how a particular value gets changed over time, but it can be very tedious as well. So it's not that. Okay, let's help again. Help running. Okay, advanced, attach, continue, detach, finish, handle, inferior, interrupt, jump, kill, next, reverse. Nope, none of these seems to be what we want. Help, status. Okay, info address, info breakpoints. That could be one. Info checkpoints, currently known checkpoints. Info frame. Okay, could be one of the shows. I know you can print the current address. So the question is, can you go from the current address back to the line number corresponding to the address? That's the question. Okay, let me explain what I mean by that. You can always say print EIP, and that's the current address. So that tells me this is already telling you this is build tree plus 8. I think that's the offset. That's, you have to find out what is the address, what is the line number corresponding to that address. That's the next step. I don't know exactly how to do it yet. Maybe a post-it would help.
Okay, I was wondering if there was
I'm not kidding. I actually mean it. Use a piece of paper. So when you stop and you want to, kind of jot down where you are at, you might want to just, kind of write down the line number, which
Okay,
file.
yeah, for sure.
So can you, if you examine that address there,
Mm-hmm.
and you examine it like as a word with I,
Mm-hmm.
would that tell you like the instruction?
Yes.
So would that work for what he's asking?
No, because it only shows you the assembly code. It doesn't show you the C code. What he wants is, where am I in the file, in the source file? So we want to map it back to the line number. I think Google may be able to help you. GDB maps address to source line number. Okay, debugging with GDB. Info line prints address in symbolic. Oh, okay, maybe that's it. Info line. There you go. So info line is the command that you're looking for, because it tells you where you are currently at in terms of the address, but it also tells you the line number of the source file. So that's basically what you're looking for.
It is. Thank you.
Yeah. Well, don't thank me. Thank Google. And whoever wrote it, that got indexed. All right. Any other questions? This is very useful. I just never really have the use of it, because I just scroll up and up and up and up and up until I find out where I stop.
Yeah.
But this is better.
I have been doing that, and I got sick of it. So.
The other thing that you guys, I'm not sure anyone has tried that, but it might be helpful, is when you when you're writing your program and your hard drive has a few gigabytes of space left at least, do a screen recording of your own session, so you can TiVo yourself. Well, think about it. Don't you think it might be useful? If you can just TiVo your whole process of writing a program and debugging your program, if something has passed already and you did not save a file, or it's too fast you could not read it, if you can TiVo yourself, you can just go back, use your VLC or whatever video player is your favorite. You can go back in time and find out, okay, what did I just do, or what was the output of the program, or in your case, where was my breakpoint? It might be useful. Okay, it's not really using up that much space, because of a 1 hour and 20-minute lecture, it only records to about 1.6 gigabytes. And I know you guys have 2 terabyte hard drives, on your laptop computers. So 1.6 gigabytes should not faze you at all. But just an idea. But I think some of you might find that useful, as you get used to the process. If nothing happens and you don't need it, just delete the file. But in case you want to trace back and say, okay, what did I just do 2 minutes ago? Hey, you got your file already there. Okay, just an idea. Okay, any other questions? Yep.
Have you decided on the format of the test?
The format of the test, I have not decided yet. We know that we cannot take it over at the lab, so we know that it cannot be online, so it's going to be paper-based. If it is paper-based, I think it will just resemble, exam 2, except the scope is also going to include the stuff that we are talking about now.
So it's 2 hours?
Hmm?
Or is it 1 minute?
2 hours.
2 hours.
It's a 2-hour exam, so the number of questions will also be adjusted accordingly. So we had 8 questions before, and now it's going to be just a little bit more, maybe 10.
So that's what you've settled on. It's not going to be multiple choice or anything else.
I'm not sure multiple choice is going to help, because if it's multiple choice, it will still be testing the same, similar concepts. So I would just give you a piece of code, and then you have to tell me, at the end of the execution, what is the value of the register. So it's instead of filling the blanks, you just choose one of the values.
Right.
Yeah. So the burden is on me to give you guys, likely but wrong answers.
Well, see, yeah, but also looking at it as we know that one of the answers is correct.
Yes.
So it comes down to our ability to interpret it, but at least we know we'll end up with possibly the right answer.
Or not.
That's assuming that I don't have none of the above.
I mean, I'm just speaking from experience. I mean, I did pretty well in this last test, but there was a couple of them where I just missed one thing and just totally failed the entire question. So at least in this case, we'll know one of these is right. Now can I,
But I'll have a catch-all too. I'll have a default.
Only
No, none of the above. That's the worst. You can almost know for sure that all of the above doesn't work. What is the value of EAX after this code? All of the above. Probably not. Well, until we have quantum computers, okay? When we have quantum computers, yes, it can be all of the above.
Well, you're not specifying the process context, so it could be all of the above.
There's a quantum processing. It can be all of the above at the same time. All right. So are there any questions about this homework assignment that I can answer right now?
What is the answer to it?
What is the answer to it?
42.
42.
That's fair.
But since I'm twice as good, it's going to be 84. All right, so we'll go back and look at the source code, and you guys can kind of scan through this and see if you have any particular question of any particular line. Yep.
I actually just have a more general question.
Go ahead.
Return value address and return $4.
Okay, that one never appears in this program because we never return a structure.
Okay.
We only return the pointer to a structure, which is a scalar, so we are still returning that in EAX and not using the return value address concept.
But those are, if you were to return an actual structure, then you would use those.
When you return an entire structure. Typically, it's not a very good idea because returning an entire structure is extremely inefficient. We do that all the time in C++ programming because it makes everything look nice. But in reality, we don't really want to do it because it's very inefficient. Because you can see we do mem copy a few times, in order to use returning a structure. So it's not efficient at all.
But passing by value and then returning that, would you use that as well?
Not in this program.
No, I'm not talking about that program, but just return value address. That would be used if you were, would that be used outside of just returning a structure? Is that just
It is
passing by
only
value,
for
returning
returning
over?
an entire structure.
Oh, it is?
Yeah. Now, your structure can be a very simple structure, it only has 4 bytes, but as long as it is a structure, it will still be returned that way. So your structure can have only one single member, and the member is an integer, but when you return that structure, it will still use the same mechanism, which is using the return value address. So the caller gives you a space to store your return value. Okay. Any other question? No questions. You guys are awfully quiet.
I'll call you later.
Yeah. I think we've got to absorb it a little.
Well, let me scroll a little bit here and see if that will help. The longest one is insert value to tree, but when you look at the complexity, this one is a little bit complex because of the conditional statement. But I don't think the conditional statement is going to be a big issue. You don't have to translate the conditional statement exactly the way it is specified in C, because you can shortcut it. Because one single comparison, one CMPL instruction, will give you the flags that you need to determine which way to go. You don't need to compare again when you do it in assembly, because all you have to do is to use the right conditional branch instructions to go this way or the other way.
Right. So I guess here's the question then. Because I noticed you've got the greater than, the less than, because we're going left or right. And
Correct.
as you said, when it's equal, it's not supposed to do anything.
Correct.
But when we do a comparison, if it is equal, we
Then
still
you
have to
skip.
create an exit.
Yes, because we want to skip. We want to specify when to skip over something.
Right.
So that means if you want to structure your code the same way as this one here, then to skip over this line here,
Right.
you will have to say if it is less than or equal to. When you get to here, then you will skip when it is greater than or equal to.
Right.
And then the rest will just work correctly, because if a number is not less than or equal to, if it is less than or equal to and it's also greater than or equal to, it must be equal to. Okay, let me say that again. Okay, so instead of, when you implement this in assembly, this will do the comparison, and the skip over or the conditional branch is going to be less than or equal to. So if blah blah blah, if less than or equal to, go to this label here.
Right.
And then over here, there's no need to compare again, because we are still comparing the exact same two numbers. So in this case, you'll be skipping when it is greater than or equal to.
Okay.
Okay? So if you do skip all the way over here, what does it mean? It means it's less than or equal to, and it is greater than or equal to, which means it's just equal to.
Okay.
So if you just do what we have been doing, skipping over, specifying the condition to skip over, by the time you get here, it is already, just being equal to.
Okay. So you won't actually, yeah, I got it.
So you don't need, there's no special consideration in this case. You can save your comparison because we're still comparing the same two numbers, and that's why your assembly code is going to be more efficient than the C code because of that.
Okay.
The only thing you do have to remember, and if you don't remember, this is going to be really confusing, is when after each action, get out of the conditional statement, because if you miss that one little part, it's going to be very confusing.
Right.
Yep. Yep.
To use malloc in assembly, do we just say call malloc and then it'll
Yep. Just call malloc.
Okay, so then we
Yep.
just have to push the right things on the stack.
Yep. Exactly. Yeah. That's basically this is the conclusion of this entire class. In other words, at this point, we know how to implement just about everything in plain C in assembly. So when you look at the C program, if it's a function call, you push the parameters, last parameter pushed first on the stack, and then you just call the subroutine. Even though malloc is not defined in your assembly code, the linker will resolve it, just like the linker will resolve it in C as well.
So, and then also for size of the structure, we're going to have a label for that too, because of...
Yeah, we have a label for that.
Too, right?
Correct. We have a label for that because last time when we talked about this on Tuesday, so let me go to the Tuesday folder. We have a label just to display the size of the structure. So instead of using size of blah blah blah, you just use whatever label name you define, to be the size of that structure. So it should all be working out. The only thing you have to watch out for, which is also something that we experienced last time, it has to do with a circular reference, is if you delete all the .o, .d, and the okay, so I'll clean now. So when you say make, it still makes correctly. Last time it did not, because the include file, okay, that the key is the include file itself. And let's see. Yep.
I didn't quite, you're talking about the size of. Size of is a function, and we're going to call that function?
No, size of is not a real function. It is implemented by the C compiler itself. It looks like it's a function call, but it's not a real function call.
So we're going to use a label?
It's an operator.
It's an operator. What is it again?
It's an operator.
It's an operator in C, not in C++, not the C preprocessor, because only C understands structures, and only C can tell you how big a structure is. So it's an operator just like plus, minus.
So when we do our assembly code, how do we do that part? Go over that?
You don't need to do it in assembly, because one of the labels, okay, let me go back to the file. This program is going to output a file, and in that file we have a symbol defined to be the size of a particular structure. So in your assembly code, you just have to use this name, whatever name you choose. Okay, in your program it's probably tree node underscore size. So that will take the place of size of struct tree node. And that's the whole idea. That's why we have this particular little program. It's so that we generate the symbols to represent offsets to each member of a structure, as well as the size of the entire structure. Because we don't have size of in assembly programming. Is that okay? All right. So one last thing. Last time when we make when we do make, it has a problem, and this has to do with it's a circular definition thing. Because okay, what is being circular here? How does make know that init node dot uppercase s requires the header file, inc header file? It wants to compile that, right? It wants to assemble that file. But when it's trying to assemble that file, it will find out that, hey, this include file is not there, and it will stop the process, which means the dependency file was never generated as a result. So it's a circular, it's a circular dependency, and the only way to break the dependency is to say, I don't want to create the main executable. I just want to create struct node.inc. So in other words, you have to make the include file explicitly once. And then after that, everything will be good to go. So if you ever have to delete the include, well, actually right now, if you delete the include file, everything will still be fine, because the .d file, the dependency file, will already tell you the dependency. Let me try that. Yep. Okay. Any questions about this? It has to do with a circular dependency. It cannot resolve, which one should I make first.
So it just gives up.
Well, it just gives you a fatal error. Yep. Any other questions? This is the only part that can basically stop you, because you cannot even get started, creating the object file. Any other questions?
How many subroutines total?
You have, I think, 3 subroutines.
3? Okay. Well, I mean, I know you expanded on the page, so it just looks a lot. My fingers go on.
Yeah, you have init tree node, which is very similar to init node from the previous sample program. I would start with that one, because it really is one of the simpler ones. Insert value to tree is one of the hardest ones, because it's longer, but it only looks bad because it's longer. But once you figure out how to do this one line, the other line is really just copy paste. Just remember that when you copy and paste, change p left to p right, because somebody in this class, like myself, will forget that and will just be appending everything to one side of the tree and go like, hey, this is not sorted. Yep.
So those labels that are made in that other file, we don't have to define those at all in our subroutines. They're already made. Like we can just
No, you have to create that file. So you have to go through the same process as what I did on Tuesday.
Okay, right. I'll go back.
Yeah, so that means, this file, you have to write this file to print out the offset to each member of a tree node in this case. Okay. Any other questions? No other questions? We all good? I think next time I teach this class, I'll use C++, object-oriented C++, with virtual functions, virtual methods. That will make it more fun.
Yeah, that would be beautiful.
As long as that's extra
So
credit.
As long as it's extra credit.
Don't try on Windows.
But I think, I think we did everything, that I set out to do, from day one. Remember what I said in day one? I said, I'm not expecting anyone in this class to have to program in assembly for a living. So the purpose of this class is not so that you can program in assembly for a living. However, you will run into problems that you cannot explain using just C. And if you mess up OEBP, okay, what happens when you mess up OEBP? Think about it.
You don't return to the right place.
When you mess up OEBP, okay, let's say main calls G and G calls F and F messes up OEBP of its own call frame, okay? Do you think F is going to display any problem?
No.
No. Will it return correctly to G?
No.
It will, because the return address is still there. But by the time it gets back to G, EBP will have the wrong value because we popped OEBP at the end of F. So by the time we get back to G, the frame pointer will be off. So now it depends on how off is off. If it's completely wrong, like the null pointer, you're lucky because the program will stop right away on the first attempt to access a local variable or parameter. On the other hand, if you just add 4 to that location, things will be very confusing because all the memory access to parameters and also local variables will only be off by 4 bytes all the time. When you intend to change variable I, you're changing J. When you intend to change J, you'll be changing K. And if you're changing a pointer, oh, it's even better. It's even more fun. Yes?
Sean has a question.
Yep, go ahead. Okay, we have a proxy. We have a proxy here. Very good.
So at the beginning of the semester, you showed us that program that you had 2 functions and it called the function that it shouldn't have called. Why did it do that? Like, how did that happen?
How did it happen? Okay. Do you remember when we talked about it? No. Or the name of the source code? No. Okay. I'm gonna give it a try here. Bad something. Okay, bad multi-branch, bad global variable. Yeah, that's not it. Well, it has to do with an array access that is off by 4.
That was like near the beginning.
Yeah, in like January, I think.
And there's a subroutine called F. I think that's the name of the subroutine. Blah. It has to go through some really big files, unfortunately. Okay, I'm going to change that. So instead of asterisk, I'm going to go to blah cisp310 because it has to go through my other classes, and some of my other classes have big files, like an entire virtual machine. So, yeah. Okay, there we go. Worst silly, bad silly.
I think it's worse.
Well, okay, but to explain that, what I'm doing is I am using the access to an array out of bound in order to modify the return address. So I'm modifying the return address by 5. Does that sound familiar? I'm decrementing the return address by 5, which means instead of going to the instruction next following the call instruction, I'm returning back to the call instruction itself. So it was a particularly doctored, example, but it does illustrate, how how a really simple C program that looks completely harmless can produce a symptom that cannot be explained at all using just C. So if you find a sample program, we can talk about it on Tuesday, next Tuesday. Okay. Any other questions? Yep.
Can you explain about allocating and deallocating memory? Because what you did is you either add or subtract the ESP stack pointer. But all it does is just change the pointer and not deallocate. Memory is still there.
Correct.
How
Okay. So what you have to do is to remember that your stack or the memory allocated from the operating system as your stack is a big binder. Okay, each page is a byte, and you have a big binder as your entire stack. What the stack pointer is a bookmark. The bookmark says everything from this point and above are quote-unquote in use. Everything that's below are not in use. So by moving the bookmark down a little bit, you're basically just changing which part of the binder is in use and which part is not in use. So when you move the bookmark back up again, the content of the rest of the binder may or may not get changed. That part depends on your system, whether interrupts will use your stack or not. Now, when we are using a protected, operating system like this, the interrupt surface routines will not mess up your stack because they are using their own stacks, the system stack. So that's why, as far as we can see, the content of that part of the stack doesn't seem to have changed at all. I'm not sure what signals will do, because signals may actually use the user stack. I don't think it uses the user stack. But in general, when you're writing programs, you cannot assume that that portion of the stack can remain intact because it is below your bookmark.
No, what I'm saying is, even though it's not in use, there's still something in there.
Right.
So doesn't that take away memory?
Yes.
So isn't that kind of useless, the allocated memory?
It is not useless. Okay, now that's a good question. So the question basically is, is this, allocate only on demand on a per invocation basis? Is it a good thing or is it a bad thing? That's basically what you're asking. Is that it? Okay. Imagine a real program. Okay, a real program probably has thousands of subroutines, right? So let's just say that each subroutine on the average will take up, 50 bytes. Okay, just a random number that I picked. Okay, when you have 2,000 subroutines, each one takes up 50 bytes. If you allocate that storage statically, how many bytes do you need? 50 times 2,000, which is 100,000. Okay. Now, do you think your program is going to have a call structure where every single subroutine is going to be in the chain? You have basically 2,000 subroutines having one to call another to call another. That's a big chain. Not likely, right? Okay, so the deepest you can go, let's say you have a really complex program. When you use backtrace, it can go up to like 100 levels, which is pretty deep. 100 times 50 is only 5,000. So that means instead of using 100,000 bytes, you're only using 5,000 bytes. So it's still saving memory. But the biggest thing about allocating on the stack or dynamic allocation, allocating and deallocating, is two-folded. One, you can implement recursion. Because if you have a static piece of memory allocated to each subroutine, then recursion doesn't work. Because in recursion, each invocation requires its own space for its own parameters and local variables. So without this scheme of using a stack, recursion will never work. But let's just imagine that you never take Professor Fox's class and you never understand what is recursion. But there are other things in life that require that too. Multi-threading is one. If you ever write a program that is multi-threading using pthread, then any subroutine using a statically allocated memory is going to have problem because two threads can try to execute the same subroutine at the same time, so they will step on each other. So that's why stack is good. Even though it seems like we are still wasting space because the entire stack is pre-allocated, it is still a better way of doing things compared to the alternative. Any other questions? No other questions? All right. So next time you have a C or C++ program that has a behavior that cannot be explained, try to drop down to assembly language. It is most likely because you have some sort of array access that is out of bound, modifying things that it is not supposed to. The EBP is one big one, the return address is the other one. If any one of these two locations get modified, especially when it's only modified by 4, by a small number, really bad things can happen. It can be extremely frustrating and confusing. If they're way off, your program just breaks. So it's okay in that case. All right. So I'll see some of you on Tuesday, and some of you I'll see over at the lab right after the class.